So, welcome to the video lecture series on principles of compiler design. In today's video lecture, we will be learning about the way of constructing a directed acyclic graph. So, it is shortly called as DAG. So, what is this directed acyclic graph? So, it is actually a pictorial representation of a 3-address code. And why we want to learn this? So, in general, directed acyclic graph is used to identify or determine the common sub-expression in a basic block. So why we want to find a common sub-expression? So we want to optimize the code. For that purpose, we are actually identifying a common sub-expression. So it is having a set of procedure for constructing a directed acyclic graph. Now the first procedure is actually all the operands has to be represented in a leaf. Okay, and if it is actually initially represented, it should be subscripted with the value called as 0. So whenever you try to use an operand on the first time, it should be always subscripted with 0 in the leaf node. And all the operators should be represented in an internal node. So if you are using any operation, mathematical operation, plus, minus, star or division operation, it has to be represented as an internal node. And whenever you get a result as a form of expression, that has to be represented in an internal node. And if you have already a common sub-expression, and if it is already computed, so simply assign a variable to that. That's it. So no need to recompute it again. So that is the procedure of DAG here. Now we will actually learn this DAG construction and we will illustrate with this DAG construction with an example. Now you have a 3-address code here. A 3-address code is having 5 different statements here. The first statement is T1 is equal to A plus B. Now the operands are A and B, and the operation is plus here. So to start up with, we have to construct operation plus here, and the left side should be A, right side should be B. But here the problem here is actually this is actually initially represented, isn't it? So A should be represented as A0 and B should be represented as B0. Now the entire result has to be stored in T1. So I try to store that in T1 here. So it has been assigned with the value called as T1. Now coming to the next operation, X is equal to T1 star C. So T1 has been already computed in the subtree. Now what you want to do is you have to take up a C value and then multiply with the subtree. So star is called as a mathematical operation. So on the left side you have T1. It should be connected with T1 here, and the right side it should have C. So right side I have C. C is actually initially represented, so it has to be represented as C0. Now this entire result has to be stored in X variable. So I assign X to the subtree. Now coming to the third one, T2 is equal to A plus B. But understand that there is no difference between the first statement and the third statement, because value does not change for A and B. So T1 and T2 have a common value here. So there is no need to construct the tree again, because it is already constructed and it is computing the same value. So simply assign T2 to T1. T1 and T2 actually represent the same common subtree here. Now the fourth expression is Y is equal to T2 star D. Okay. T2 is already computed here. What we require is actually we have to take D and multiply with this T2 here. So star is called as a operation here. So I make star. On the left side you have T2, on the right side you have D. Since D is actually initially computed, so I represent that as D0. Now finally we will take the last expression. We have array added with T2, and that result has to be stored in Z. Now array has to be represented. So when you take up an array is actually represented with square bracket. Square bracket is an operator, so it should be represented as an internal node. On the left side of an array you have M, and the right side of an array you have I, isn't it? So M should be represented in the left side and I should be represented as on the right side. But nothing wrong if you mention it as M0 and I0, because initially it is getting computed. And now you have an array, and this array has to be added with T2. T2 has been already computed in the subtree, isn't it? So M of I should be on the left and T2 should be on the right. So plus should be as an internal node, and I have M of I on the left side and T2 is on the right side. Now this entire result has to be stored in Z, isn't it? So I just make it as Z here. So thanks for watching a video. Have a good day.